All right, welcome back to Vere Part 2, the Loom and the King. This is part of Vere, but to some degree, the kinds of things that I'm talking about today will also carry over to Aries, since Aries is a serf and has to do similar kinds of allocations for things. I decided, originally my plan was to spend 3 lectures on the runtime and have a third lecture that would be primarily dealing with the IO drivers, con.c, and some other portions. But I've decided to refactor all of that into the veins discussion. I have like hiccups. Into the vein discussion and just do veins from here on out. So next week we'll take a look at vein and dill, and then we'll have our assembly break, and then come back and look at aims. Aims and clay and air are kind of our giant veins. The other veins are all relatively straightforward compared to those 3, so we'll hit those pretty quick. All right, let's pop over to VS Code. Let me get a chat and everything open again. The homework from last week should be, I think, reasonably straightforward. We decided to go with having you link, like basically write some kind of a little C program that ends up declaring an atom and then needing to free it, just to get you used to the pattern of what reference counting looks like. Now, today we need to talk about the loom. And so this is the main memory model of Vere. And I think the reason it's called a loom, as far as I can tell, is kind of a mixed metaphor, because of course a loom consists of a grid that you shuttle back and forth across. That's one of the distinguishing features of it. And Vere's loom is structured along what's called the road model. And so you have a road going one way, and then you have an inner road that goes a different way, and an outer, and a more inner road that goes a different way, and you nest these pieces together. The basic concept of this is that we're going to have let me give you a visual at least here. We're going to have a contiguous block of memory, which was formerly 2 gigabytes, because that's what you could do in 31 bits with the pointer that has the 1 bit reserved. But now you can specify it by the runtime, and you have a little more flexibility on what you can do with it. So we're going to call this the loom or the noun arena. And to work on it, we're going to need to use special U3 allocators. So that was U3A. These are our, let me actually pop open, allocate.c. So this will have equivalents like U3A malloc, which is kind of like regular malloc. There's some discussion of why not just overload regular malloc. And so when you call any malloc, then you're calling U3A malloc. But there are some parts of the system manager outside of the loom that do use malloc, and so you'd run into some weird ambiguity if you did it that way. So right now, if you're going to do anything on the loom, if you're going to create any nouns, you have to allocate specifically in U3A. You're not going to do that often. Most of the time, you're going to use I, which is imprison.c, which is how you create an atom. So you would write a certain number of bytes to an atom, for instance, and it would generate an atom for you, or some other kind of noun. And then to read out of this, we have U3R, which is retrieve, and U3X, which is extract. You do something similar, but going the other way. You pull the value back out into an array. The difference is that extract will crash if it fails to read. U3R will do a soft fail. And so you can do a crash handler for this. Anyway, Okay, so one way of organizing memory. So if you're gonna have memory on a computer, one of your fundamental problems is how do you organize this in such a way that you don't have lots of unusable gaps in your memory. You allocate something, you allocate something else, you delete the first thing. Now there's an unallocated block at the beginning of your memory space there. And if you've worked with old systems, you remember having to defragment hard drives, for instance, because you'd have to copy everything into contiguous blocks. You don't want to use non-contiguous blocks because they're not as fast. If you have a system, a file system or a memory system that supports that, then you reach a pointer at the end and you have to do a jump to a different place in memory and read out another block, and things can get quite complicated. The standard model that's used by modern operating systems is to have a heap for manual dynamic allocation. In C, this corresponds to malloc, so we're just doing a memory allocation here. And then a stack, which is basically local variable data. You can do explicit allocations on it in C, like with alloc A. The heap grows from the bottom up in a memory space, and the stack grows from the top down. And as long as you don't meet in the middle, you have enough memory. That's kind of your setup there. Stacks are set up so that they're last in, first out. You're just building values up and down the stack as you process an expression, for instance. And then heap you build as you need to. When we look at the road model that's being proposed up here at the top, notionally, we can see that there is a block here at the beginning consisting of heps, which is our heap. There is a BRK. This refers to a BRK was a System 5 Unix call to mark the limit of the heap arena. Limit of heap arena. And then on the other end, we have a stack pointer marking, anything above that is occupied stack, anything below that is free memory that we can allocate into. U3 is going to differ from this model in essentially, by defining the limit, it's going to have one difference, which is we're going to allow the heap and the stack to point either way, which means that we're going to be able to do this neat nesting back and forth. And so what we're going to end up with is a model that looks like this. Okay. And we're going to have a surface road that has a heap low and a stack high. And then when you're working on an inner road, you're going to have the stack low and the heap high. And everything that is outside of the road, those SIGs, those tildes, is considered to be immutable memory while you are working on that inner road. And there are some neat bits of determinism and some neat bits of efficiency with memory management that happen from these properties. So for instance, you don't need to keep track of reference counts in senior memory. If you're working on an inner road, you only need to worry about the reference counts on the road that you're currently on. And you can nest roads all the way down. We'll look at a north-south road and a south road in a second. You can keep nesting roads, invoking new roads. And then you have this block in the middle that is free memory that I've represented by axes here. And there's a PAM in the center of that, approximately in the center. That's called the guard page. And if your heap moves up into the guard page, then it will reallocate the guard page in the center of what remains of empty space. And so it'll be moving around back and forth as you allocate these things. Now, the main advantage that you get from this is that because you are limiting all of your changes to an inner road at any given time, you can consider the outer roads to be left clean. So there's an idea of a clean page and a dirty page. And so you can more efficiently navigate and allocate memory when you're working with this. This also works against fragmentation, because everything that you're doing is in the middle of this memory arena and can be cleared at any time. If a calculation crashes, then we just throw away the inner road. We don't worry about it anymore. Now, before we get into more details of that, we're going to look at the north road and the south road. So this first one is a north road. The second one is a south road. All right. Tildes are contiguous memory, or excuse me, immutable senior memory. And then the rut to the hat marks the heap. And then the mat to the cap on the other end marks the stack. And then you flip it on a south road. The other neat thing about this is, and this is a little bit elided by this diagram here. Hello, Ted. The other neat thing about this is that when you clear this inner road, so let's say you're on an inner road here, this is a north road. When you clear it, this part of what is the inner road's heap, or excuse me, the other way, this part of what is the inner road's heap becomes part of the stack on the outer road that contained it. And so you can automatically keep the variables that you want to keep inside of an inner road. And then if you want to keep migrating them out, you'd have to copy them to your heap in each inner road to work your way back out as you step back out of this. But by swapping those directions, then you get those nice guarantees about what's clean and what's dirty and everything. The upside of doing the reference counting this way is you do get deterministic finalization. What this means is that if you are pulling in and declaring reference counted variables, you're keeping track of them on an inner road, then when you free them all the way, when the reference count goes to 0, this happens as a result of the property of the computation itself, not from some other sort of non-deterministic preemptive event coming into play here. So you get nice automatic memory management, even though you have to do manual ref counting. This yields an eager determinism for you in determining when something can be freed in terms of what's going on. Now, one of the questions looking at this is, when do we use a road, right? Like what does it mean to move something to a road? So the surface road is reserved for essentially for immutable parts of our system, like the things that we want to leave clean. We don't want to mess with. We're going to do snapshotting. We're talking about that sort of thing later on. We don't need to worry about the surface road changing effectively when we do this. An inner road can be aborted at any time. We can enter a calculation. We can throw it away. It doesn't affect more outer roads as you do this. And so this keeps you from fragmenting. When you are on a road, well, okay, so in Arvo and in Vere, essentially, a new road begins in the cases where, let's see, every event, every attempt to process what will become a new event, right? It's when it completes, it becomes an event, starts a new one. Every read from the namespace starts a road and calls to Mink, Mock, the other virtualized operators there. Those all start inner roads. Now the road model is a Vere convention. Of course, Arvo doesn't know about this. Oh, go ahead.
I'd actually like to clarify this a little bit.
Yep.
When you're in kernel space, so like if some code in a vein is running, the vein is past a gate. It's of type roof, if I remember right.
Mm-hmm.
So Arvo, when it calls the vein, passes in a gate. That's the Arvo's scry gate. It's like the Arvo scry handler. And so veins can actually just call that gate directly without using .ket. So veins do not .ket because there is no scry handler when you're in kernel space. Like the kernel is the thing that provides a scry handler gate. And veins, because they're in kernel space, can just call that directly. They have permission, so that it's okay for them to see, the internals of that gate, like all the data that it closes around. Whereas for user space, they're not allowed to see that, right? All they can do is send it a path and get back a response, but they can't know the internals because it might include like your private key. But that means that when the kernel does a read from the namespace, then it does not create an inner road for that engine. But when user space calls .cat, that does create an inner road.
Okay, so when we say every read from the namespace, we mean user space .cats.
Yeah,
specifically here.
that's right.
Okay, that makes sense.
Yeah, and it is odd because if you have when you go into an Arvo event, you create one inner road, right? And then if you Gall calls Mink to run user space, like to run an agent. So then you're in another inner road, which is a user space inner road. And then if that inner road runs a knock 12 through a .cat, then that creates another inner road inside of that, but that's actually a kernel space inner road where it's running the kernel's scry handler. So it's like kernel and then user space and then kernel again. There's like home road and then kernel space out road and then user space road, and then the innermost road is also back in kernel space when it scries, like for the scry handler. So that's a little weird thing. I didn't really realize that that's how it worked actually until maybe a year ago. It's sort of counterintuitive. But anyway, just to kind of give some color there.
Do you want to say anything about the copy outs that happen when we declare on our heap and then it ends up in our stack and we have to copy it back over? Does that happen a lot? Where we passing these values back out by multiple copies?
I mean, it happens whenever you leave an inner road, right? So in most I think the majority of the inner roads that we create are running a Gall agent, right? So every time that Gall runs an agent, it creates an inner road to run that agent. And so every agent activation ends by a call to U3A take that takes all the stuff from the inner road that is still needed and copies that out to the outer road. So that's mostly when it happens. There are a bunch of other times when it happens, but that's, I think, the most common.
Mm-hmm.
I don't know if there's other parts of that you want me to.
No, I think that's fine for, we're going to keep kind of circling around. I think probably the next thing it makes sense to take a look at here. Well, we'll go to U3A in a moment. Before I get there, let me make sure everything about okay, so the loom is made of pages, 16 kilobyte pages. I was talking about the guard page a moment ago, and so everything is divided into 16 kilobyte chunks. Yeah, when a fault is detected in the guard page is recentered in the free space of the current road. Excuse me. If the guard page cannot be recentered, then memory exhaustion has occurred. There was also some discussion, Ted, you might know more about this. There was some discussion about adding a raw hint to suggest when to use a new road.
Yeah.
What would
I
be
still
the
think that's a good
advantage of
idea.
that from Arvo's side?
Well, there's sometimes when you don't really want to affect the execution at all, other than say, hey, jump into a new road just to have more efficient memory management, right? So like if you know that you're about to run some function, right, that where that function is going to create a ton of garbage and then return something small, then it would be advantageous to run that in a new inner road, because instead of needing to do a lot of ref counting type stuff in the outer road, for now you still have to do ref counting on the inner road, but basically that last step where you do the U3A take to copy the data from the inner road back to the outer road, that only copies the data that's still needed, basically like the return value of that function. And so if you're going to call a function that like does a lot of internal stuff and has a lot of internal intermediate variables that it stores, ephemerally and then only returns something small, then garbage collection, meaning like you only copy out the result, but you just don't bother, marking all the garbage as freed, is more efficient in that situation. And so that's like you can think of the copy from an inner road back to an outer road as a garbage collection step. Whereas normally we don't do garbage collection. You can call it a moving garbage collector or a copying garbage collector, moving GC. So that's a pretty standard design that a lot of systems use. And we don't usually use that. We use reference counting. But in this particular case, we do use a garbage collection algorithm.
Okay.
And yeah. So that's why it would be useful to say, all right, we don't care about catching errors, which is the other thing that you can do. Well, you can do two other things in a row, right? You can set a scry handler and you can catch errors. Right? Like those are the other reasons to call mink. The other differences between mink and just a .tar where you run raw knock. Right. Yeah. And so, or just, executing an expression, right? Like something similar like inline Hoon code, right? Not inline, but just like normal Hoon code. So there are just places where you might want to say, hey, for this sub-expression, do it in an inner row so you can get that garbage collection at that particular boundary. And right now there are places like that. And what we do is we call, I think there's a function called road or maybe Muir in Hoon.Hoon. Let me pull it up.
Yeah, I've just got Vere here.
Untyped unitary virtual. Yeah, so there's Muir is pretty close, where it just actually mole, I think, typed unitary virtual. Yeah, it's unitary, meaning like if it doesn't work, you just get a unit, like you just get a null instead of getting a stack trace.
Okay.
Oh, there's also a road. Yeah, there's a road gate in Hoon.Hoon, line 11381. Yeah, and that takes a trap and runs the trap.
With a mule, so you're forcing a new road.
Right. And then if it crashes, then road crashes. If the code that you're running inside of that crashes, then it crashes. So it runs mule, which normally, if the inner code zaps, crashes deterministically, then it'll return a stack trace. Mule will actually return a value that says, no, pair of no and stack trace, as opposed to pair of yes and value, where it's an each. But in this case, road wraps mule, it calls mule, but then if mule fails, then then road zaps again and puts it propagates the stack trace. So it crashes with the same stack trace that mule did. So what this does is it says don't do anything differently other than do the subcomputation in a new road. So it would be kind of nice to have this as a hint instead of as a knock function call. It's not really crucial, but
yeah,
it would be nice.
Well, and this is kind of going back to what I was saying earlier about how it's the properties of the computation that give you the automatic memory management, right? That give you the garbage cleanup in this sense, because only the result that you're getting back is the thing that matters. Everything else gets automatically cleared when that road closes.
Yeah. If you're interested in this subject, it's an interesting subject, and there's a great paper on it. It's very accessible, called A Unified Theory of Garbage Collection. And it places both reference counting and garbage collection algorithms into the same kind of mathematical formalism, and shows that they're categorical duals of each other. And then goes from there to describe how that duality affects when you want to use reference counting versus when you want to use a GC. And so I found that very helpful in kind of getting oriented in this whole kind of world. When do you want to do one versus the other? And in practice, almost all production systems are somewhat hybridized between reference counting and GC. So ours is at the moment, Vere is mostly reference counted, except for this GC step here that we do in U3A tape when the inner road exits. There's a question from Gary about
Does
uh,
Aries use roads?
so the answer is not exactly, but Aries is a very similar system. And their opinions differ about exactly how similar these systems are. Um, but they certainly look a lot like one another. So uh, Aries has, instead of rows, it has what they call two stacks. So basically, instead of a stack and a heap, um, it has two stacks, and that's it. And each time, and the way it works is that each time you sort of make a new frame on your stack, which roughly corresponds to a function call in a more traditional system. Like in traditional systems, like in C or most languages, like you only push something onto the stack, onto the call stack, when you call a function, and then when that function returns, that pops the stack frame off the stack. And so you can imagine doing that in different ways with knock, right? You could say maybe each opcode could be its own stack frame, roughly. You could get kind of close to that, right? Or you could say it's each knock 9 that does fires an arm in the core is its own function call. In any case, or is its own stack frame rather. I don't remember exactly where Aries has landed on this question. I think the answer is somewhat complex, but I think it's somewhere in between like every opcode and every function call. But the Aries stack frames are more granular than Vere's stack frames, which are you only from the perspective of then they're more granular than Vere's roads, I should say, because you only make a new road in Vere when you're virtualizing, whereas with Aries, it's more like each knock 9. I think it's even more granular than each knock 9 pushes a new sort of like little micro road onto the stack. And then another difference is that Aries does not use reference counting. And so each stack frame has what's called a bump allocator, which is a different kind of memory arena, where all you do is you know what the start of the memory arena is, like where in memory that arena starts. And then you have another value that you store that stores the like high watermark of like how, what's the highest point, right? So you know the lowest point and the highest point of the memory allocator of that arena. And then whenever you want to store a new thing in the arena, you just add it to the end and you bump that, field up by a bit to say like, okay, now we've gone from storing 37 bytes to storing 39 bytes, right? More words really. The nice thing about a bump allocator is it's basically the fastest kind of dynamic memory allocator you can have, because it doesn't do any bookkeeping other than updating that one field that says how big it is. And so within each stack frame in Aries, there's a bump allocator. And so as you're kind of going along and running some function, right, like doing some opcodes, you're just, each noun just gets appended on the top of the stack frame. And there's no reference counting, so you don't have to store the ref counts in the noun representation there, and you don't have to mess with them, and so you don't have to, so that reduces the number of operations that you have to perform, and makes everything condensed, so it increases the cache locality, and reduces the number of cache misses you're going to have. And then also, because it's doing these more granular road transitions, basically these little micro road transitions, each time one stack frame pops in Aries, it does a copy and garbage collection down to the lower stack frame. And so all that stuff that you bump allocated in the stack frame as you're running it very quickly, you only take the value that you care about, and you recurse through that and copy that back to the lower stack frame, which is on the other stack, right? So it bounces back and forth from the left stack to the right stack, back and forth. And what's nice about that, so it's a little tiny copy and garbage collector that happens like very frequently. So that maintains the determinism of that Vere's ref counting has, right? Where like the memory usage and the memory layout is deterministic. If you go and run the same thing a second time, you'll get the same memory layout, which is really nice for forensics and also in general for having predictable performance. And this is one of the major downsides of garbage collection in general, is that typically it's just triggered on a timer or some sort of heuristic, which means that the performance is not predictable. And that lack of predictability is a huge problem for production systems, right? Like it's often much better to have something that's fairly slow, but is never very slow, and you know exactly what the worst case is. And it's sort of like having insurance, right? Like your expected value whenever you have insurance is lower, but the variance is also lower, and so it's usually worth it, or depending on the context. So anyway, you usually lose a lot of predictability when you use garbage collection. But because of the way that it's done in Aries, where it's not triggered heuristically, it's triggered deterministically, then we've maintained the deterministic memory behavior that Aries has, but while getting the while getting the performance benefits of garbage collection, where instead of, and the unified theory of garbage collection paper goes into this, that one of the big differences between the two approaches to memory management is that with ref counting, the amount of memory that you have to modify and the amount of computation that you have to do is proportional to the total size of the memory that you've allocated, including all the garbage. Whereas with garbage collection, you only have to modify the complexity of, the computational complexity is only the size of the data that you're keeping. And so for a system like ours that's creating lots and lots of cells all the time because it never mutates anything, right? And this NOC creates like tons and tons of garbage cells, like nobody's business. Even other Lisp and Haskell systems that have similar basic data structures actually can't handle the load of cells that Vere's allocator can handle. They fall over right away. So we have tons of garbage, which means that we need to be able to allocate lots of cells efficiently. So the bump allocator should be good for that. And then we also need to be able to do the bookkeeping on that efficiently. And if we can take only the stuff that we actually need and not the garbage, that helps a lot. So those are some of the design principles behind Aries. Aries is 2-stacks interpreter. I think there are some others that I'm less familiar with. So, I'm not fully authoritative on this question. You'd have to ask Edward Amazon to get the full story, but I know that's part of it. That's a big part of it. Gary, you were asking, but would it still be able to make use of the new road hint the same way? I don't know. It's a good question.
So I guess to preface my question, I need to quickly explain the snapshot system. And so this is, whenever you start a fake SOD, wherever I am. Let me start one here. One of the things it does up front is it plays back. Well, it didn't do it here. I must not have had anything logged there, but it'll play back a certain number of events. Maybe that must be what that number is there. So I actually hadn't done anything since the last snapshot. And so every few minutes, Vere saves the entire loom and writes it down, and then it continues to update the event log, but those events in between the snapshot and the event log have to be replayed to restore it to its present state. And it's whatever U3 save decides is the relevant information to save there. So I guess the question there is there compatibility between Vere's notion of snapshot and Aries' notion of snapshot?
No.
Because those just look different from each other.
Yeah, so Aries uses a very different system. So that, there are a few different components to something that can run Arvo, right? An Earth process. A Mars process is the new name for it, or used to be called a surf process. It's a NOC worker, right? But not only is it running NOC, it's running Arvo, really. And so, which means that it's running NOC and also persisting the Arvo core in some way, right? And it's a prevalence system, so it uses an event log and snapshot model. and all of Urbit is designed around that. So you're going to have some kind of event log and snapshot model, no matter how you build this thing. But that's a very broad statement, right? And there are lots of different ways to build that. So Aries still does have event log and snapshot, and it may use actually, I was just reading a thread about this. They're not going to use the epoch system initially in Aries because it would maintain two. The way that's implemented right now, it maintains two snapshots, and that might get big with Aries, and so that won't do that. They'll build something like the epoch system later, but that's so it's right off the bat. It's going to have a different way of managing snapshots. The event log, I think they're going to keep the same thing, because that's not really that's not going to be any different in Aries as far as I'm aware. But the snapshots will be different. And basically, when you're building a Mars process, right? Like Vere has a Mars process. Aries is only a Mars process. It doesn't have an Earth process. It'll use Vere's Earth process, and that's why it used to be called New Mars, right? Because it's going to be the New Mars process, as opposed to the Earth process. So then we got renamed to Aries, which is a better name. But that is why it's called that. So it's that Mars process has a few different components, right? It has to interpret knock, right? So for Vere, that's the loom with the road system, and Vere's bytecode interpreter. Aries will have its own bytecode interpreter as the initial version. And then they plan on eventually writing a custom machine code for it, or sorry, custom machine. Sorry, they eventually plan on writing a knock to machine code compiler, so that it runs straight machine code as opposed to interpreting the custom bytecode. That should be a bit faster. So that's one piece of it, right? So Aries is using two stacks for that, and they're working on a bytecode. But then also there's a persistence question, because it has to do these snapshots, and Vere has a very particular approach for doing snapshots where it's all based on the loom, so it's snapshotting the loom, and whereas with Aries has its own new system called the PMA, the Persistent Memory Arena. And so it's actually separating from the beginning ephemeral knock execution in the two stacks, right? So you have these two stacks in memory somewhere that are going towards each other. And then basically whenever an event finishes, the result, like the last stack frame, will be, I think, copied into a persistent arena. Right? It'll mutate the persistent arena, right? So it'll be like another U3A take kind of thing. But instead of copying into a road, ref counting, it's copying into another allocator that's not ref counted. And that allocator has its own persistence system that has its own B+ tree, and its own memory mapping, memory mapped file system. So Vere also has one, but it's different. And Aries is designed from the beginning to handle large amounts of data, manage it efficiently. And so in order to do that, you need this B+ tree, and you need to separate the ephemeral and persistent noun allocations. So
Nikolai asks about the snapshot. It's essentially just what is the current state of the loom?
Yeah, I would say a snapshot. Yeah, a snapshot does contain the whole loom, but when you go to write a new snapshot in Vere, it only incrementally updates the previous snapshot. So if you only changed, a few pages worth of memory compared to the previous snapshot, you don't have to go and overwrite the full 2 gigabytes of loom. And actually, you don't have to write the full 2 gigabytes anyway, because it just stores the outer road, the home road, because none of the other roads are persistent. Those are all ephemeral, and then they all exit before you take a snapshot. So we only take a snapshot in between Arvo events, and the system is quiescent. And only the home road exists. And so we only have to snapshot that home road. That's the only stuff we have to persist to disk. And then as an optimization on that, Vere tracks which of the pages of memory within that home road have been dirtied since the last snapshot was written, and it only overwrites those pages within the file. And there's a system of patch files that's used to ensure atomicity of that overwrite.
Yeah, this is one of the places where you actually do start to care which road you're on more than you do. So for instance, if you're in a jet, you have a pointer to the current road, but you don't have to care in a lot of Vere which road you're on. Some parts of Vere, like the snapshot system, you do. And it actually makes a difference for a few functions like C3 assert. Other parts are pretty agnostic.
A lot of stuff in Vere is different based on, at least, a number of things are different based on which road you're in. So, like, because one of the big important invariants of the road system is that you only have to modify ref counts on data that's in the current road. If you have data that points to an outer road, right? So if you have a cell, let's say, in your inner road, and the head of that cell is a pointer to some atom, indirect atom that's stored on the home road. When I create the cell, normally, I would have to increment the ref count of the head of the cell, right? Because now this new cell is pointing at it, right? And so that's a new reference to that value. But if that value is stored on a senior road, right, or a road that's further out than the current road, then you don't have to do that. And you don't do it and so basically, inner roads can't modify outer roads. And the only time that they do is when you do the U3A take and you copy the values that you care about. And so that's a way it actually minimizes the amount of ref counting that you have to do, which also increases, minimizes the amount of minimizes the number of cache misses that you're going to get, right? Because anytime you go and mess with memory, that's a potentially expensive operation. So you want to minimize the number of places that you're modifying in memory, and so that's a very important optimization there. And it's not just an optimization; it's like a way of sort of maintaining sanity, right? Where you have this nice kind of stack discipline. Everything kind of goes inward and then back out, and you can only do this because Nock's memory model is acyclic, right? You never have a noun or a different point where the head it points to the tail and the tail points to the head, something like that. Or you never have a memory cycle where you can follow a bunch of pointers around in a circle and repeat it. Because there are no cycles in that, right? This is a way of, then you can say, okay, well, now we can have these roads where there's nothing in the outer road that ever points into the inner road. And so because of that, then you can say, all right, well, we don't even have to touch the outer road if we're doing something in the inner road. So I like to think of this actually as it's an interesting kind of example of like why an acyclic data model is useful, right? Because that constraint allows you to make various optimizations and simplifications of the execution system.
The Daimladrat says, zooming out for a second, what exactly does Vere allocate on its stack and on its heap? So at one level, right, your heap is your malloc variables. It's the things that you've manually said, I'm measuring an amount of space for this, I'm placing it on the heap, and it persists until I free that value. and your stack are your essentially your local variables, right? The things that we're just declaring here, and at the top of whatever function we're doing, and then operating on that don't require that. That's kind of your conventional C distinction between heap and stack. Or in C++, like new and delete apply to your heap.
Does this mean, Neil, that like do all cells get allocated to the heap? Like where goes all the actual like stuff that's used for Hoon and for Arvo? Like does that go all on the heap or what?
I mean, something that you have to, well, okay, so let's walk through one. So what happens is, you're in a jet, you're in some jet, and you run U3I words, okay, or U3I word or U3I byte or chub or whatever one of these variants is. And where that takes you then is here, copy A words from B into an atom. And so this will actually have to do, so this will run through slab, which is, it's all going to be a handler, and it's ultimately going to take you to U3A slab here. U3, or slab. Maybe slab is an I. Where's the actual definition for slab? I thought it was an A, but maybe it's an I. Q3I slab. Yeah. Okay. So let's go back to imprison. Well, these are all getting passed around. Anyway, what happens is you ultimately U3A malloc the block if you're talking about something that is an atom or excuse me, a noun, right? So something that is a noun that we are manipulating has been declared using malloc, which means that it is part of your heap. It's not one of the C3 types, for instance, that gets declared in a particular place. So if you run U3X or U3R to get that value back out, then that value can live on your stack and you can manipulate that value on your stack. But the value that you malloced or that you imprison lives in your heap then.
And so is this like split along particular lines? Because like with Hoon being statically typed, you could imagine like if there are simple variables that you're using, like, if Vere has to allocate something for a particular function call, where it knows that it's going to be like, okay, here's just these variables that like it's just using like 2 PAT-UDs or something, and that's in a cell. Like that could ostensibly be some sort of stack allocation, right? Whereas if you're doing a list, that would be like a heap allocation. I'm just wondering kind of how it determines how to do that.
I think there are a few like jets that do some stack allocation as an optimization. And then I think also the bytecode interpreter, I believe, does a fair amount of stack allocation for like local variables for handling like an opcode. I think it puts a bunch of those on the road stack. I could be wrong about that, but I think it does. And then I think it's I don't know exactly which values it puts on the heap, but I think it's basically anything that's sort of like a return value, from an opcode, gets put on the heap. I think my impression generally is that I remember Joe talking about this, that like Vere probably could do a fair amount more stack allocation than it does. But it's an optimization that we haven't really pursued very much, except in a few circumstances. I could be wrong about what I said about the bytecode, but that's
So
my
mostly
impression.
just does heap allocations. Like when you run knock, it'll just like it needs some cells. It'll just throw those on the heap.
Well, right. Like you look at add here, right? So look at add. What happens is you're receiving two atoms. So those are both on the heap. You are unwrapping them using U3R. And because these are multi-precision, you don't, they're big nums. You don't know what that's taking up. You have to pre-allocate that space. So that's going to be on the heap as well. And then you clear it here.
Right.
So you
okay.
could get away with let's actually take a look at the RS. Like RS, you have the advantage that you know how big the value is. Right? Like you know that you're not going to overwrite a 32-bit. Well, actually RH. Because RS 32-bit, you could still no, you could still be an indirect atom, but RH in principle you could do everything on the stack and not have to worry about what's going on with any particular operation here. So it looks like what actually happens is you get three atoms, A, B, and the rounding mode. And then it looks like it's actually okay, yeah. So you're pulling the value out into a local union. These are soft float unions because we're using software floating point. So this one is getting away with doing everything in the stack, but it's because you know the bit width. You have a guarantee here.
Yeah, so in general, because atom bit widths they're unknown. Like they could be any size.
Right. So it's not
a lot
just
of this has to be done on the heap.
Right. It's not just cells, right? Like you're referring to cells. You do have that problem with cells, but you also have that problem with atoms.
Right. Yeah, that makes sense. Okay. I think that helps to explain it. Thank you.
And so I'm actually curious. Let's contrast. So this one is really simple for half precision because it's 16-bit. If we look at the same operation in here, well, okay, so U3R is actually papering over what needs to be done there. So that's
Yeah, I mean
Oh,
all the basic non-allocation routines allocate onto the heap. If I remember right. Right. Like,
yeah, so we actually
like
would
if
have to do
you
something
U3NC or like make a new to make a cell, right? Anything like that. Those all heap allocated. So like if you kind of don't think about it, right, and you just like use the basic non-manipulation routines, it'll be heap allocated.
Well, and this is one reason why. So there's a sense in which the naive way to approach writing, like jets in U3, for instance, would be for jets to call other jets frequently. But the problem with that is that you end up with a lot of, okay, maybe I unpack something from being a noun and I make some decision about it, and then I repack it into being a noun so that the jet can unpack it from being a noun again. And you end up with these weird patterns of writing things in and out. And so some of these actually also just have utility functions like met that you don't go call the jet met, you just call a local met that solves this problem for you. Is more efficient in that regard. So it's playing a similar game. It's not exactly the same game. It's playing a similar game on avoiding U3 when it doesn't need it.
And so that's why all these jets have there's kind of like the outer unwrap routine and the inner routine. It's like the inner routine is used by other jets, but the outer routine is used by like Hoon calls.
I mean, I don't know if that's why.
I mean, that's
it is a consequence.
Yeah. It's at least useful for that purpose.
No, that's not why. The reason for that is that the basic jet interface is that you jet a core, and so there are two different functions by convention in the way that you implement a jet. One of those functions takes in the core and then extracts usually the sample slot, maybe also another slot, right? If it's a closure, like get by, right? And there are two different, there's like the map that you're getting by and also the key that you're looking up. And those are in two different slots within the noun, right? Within the core, right? So it can be that. Right, so that jet for get by will like that's what it does. It's passed in the core, and then it extracts the slots of the core that it cares about. And then once it's done that, then by convention, there's another function in the jet file that just takes in the like sort of actual arguments. So it's a C function that takes in two nouns, the key and the map. And so that basic jetting function that takes in the core extracts, those two nouns, and then just calls the other function that, with those two nouns, with the key and the map. And so that other function that doesn't take in the core, that's the one that's also useful for calling. You could call that from other parts of Vere. Does that make sense?
Yeah, absolutely. So it's like one needs to take the core, and the other actually has like it looks like the C version of that function. Like
Exactly.
add would just take the two nouns into the atoms.
Right.
Okay, gotcha. Thank you.
Let me actually contrast then. So this is regular Hoon add jetted. And so you've seen us do this before with, we're extracting at sample 2, sample 3. So this is actually doing the adjustment. So this is actually 12 and 13 because it's pulling inside of the sample from whatever noun, the core that it received, and then it goes ahead and it calls this. Right now, the jets and Aries look a little bit different, which is they receive what we're calling the subject as a noun. And then you unpack the sample here at the top of this function is what's going on. And then there's a number of different checks and stuff you have to do because it's Rust and it's really messy. But ultimately, like if both of them are direct atoms, then you can just return the result of that operation as a noun. But all of that check takes place here because you don't have to do that ref counting and everything to make this part of the system work. How is that going to look compared to, I guess the difference is like we are just receiving the core as the noun, like what we're calling the subject here is the core. We're just doing all the unpacking and the checks in the same place as where we're using it instead of what was happening here with the two-step. Aries doesn't have a jet dashboard really yet though, so we don't actually know what the interface is going to have to look like yet, so we may have to rewrite some parts of that. Go ahead. Did you have a question?
Oh, no.
Okay.
Thank you.
Ultimately, these, let me see. Let's see if there's a good example of a U3A. U3. They've moved. Yeah, they've renamed some things. I was basing my notes off of u3.md, but that's actually been changed here. I'm looking for Mint. Yeah, okay. They've all been renamed into these U3I functions is what happened to them. But so you have an interesting problem when you're declaring atoms, right? So here's your I guess this is basically what was referred to as slab. So we want to produce a block of contiguous memory on the loom. And so the two approaches are, one is we can declare it being too big, which is to do U3I slab malt. And the other is to do it exactly the right size, which is U3I slab malt measures itself and then trims off the additional values that you don't need. And U3I mint means you're specifying the size. Yes, that's what's happening with those two. There's an interesting wrinkle here, which is that everything in Vere head trims zeros. In fact, the parser actually won't even let you write leading zeros. You know, you can force it. There was actually an interesting bug that was discovered the other day that was sort of tangentially related to this problem. One of the CryptoJets didn't end up being exactly this, but it was related to it. But you don't have leading zeros, and so you know you can declare a whole slab of memory, but you know whatever leading zeros you have on there are going to disappear, which, like I said, can lead to some interesting problems if you actually want to preserve those. Some binary algorithms require long blocks of zeros to be correct. Nikolai, who just dropped off, has run into this with the gzip implementation, which needs leading zeros to mark some of what's going on with the standard format of a gzipped file, for instance. With the linear algebra stuff, you know, if you want a matrix of all zeros, you end up having to pin an atom at the head to make that viable, so you can actually keep track of that thing. So the U3 allocator, it will auto trim for you, and even if you don't trim, you just end up with an invalid atom that'll still get cleared out when it actually does an operation on this. Yeah, so allocate, imprison, and retrieve are kind of your main ones that you want to care about there. All right, the other piece that we want to take a good look at is what's going on with event logs and snapshotting. All right, so what actually is the event log, right? Like conceptually, we know what an event is and we know what the event log is. On disk and in memory, what the event log is an ordered list of all of the Arvo events resulting in the present state. So all of the completed moves, every completed move receives an ordinal number and gets written into this LMDB database that you can use. Events get handled at two levels. So there's the event log, which every event receives a write, and it's a very write heavy part of the system. The Loom snapshot then is just a picture of what is your present state, and then you can play back those subsequent events against that current state to rapidly recover wherever you're at a given time. The event log, before we look at the event log, I wanted to look at the error handling, because we do run into that very quickly when we start looking at these kinds of validations. So that's error.h, and U3 assert X here is our definition here. So functionally, what U3 assert is going to do is it's going to cause the bail, it's going to cause a crash and dump back out based on whatever happened. You know, if whatever you get back is not valid, if you don't get that zero back, then it's going to crash, flushes standard error, fprintfs, and then runs U3M bail. So U3M bail is our primary crash handler. We glanced at that one previously. Yeah, there's U3M bail, but it has a number of error codes that show up. Oops is the one that happened with U3 assert, as we just saw. But there's other kinds of things that can go wrong with it as well. By and large, these basically mirror what's going on inside of Arvo, which has some similar, like you can have like an evil vein and some other things. Or excuse me, evil base. there's an interesting convention that you run into as you start working with these files, which is that oftentimes it will give you the definition of what is being expressed in the C code in Hoon code in the comment preceding the code. And so sometimes it's actually quite complex, and you get entire cores that are laid out. It's probably not an example in manage, because manage doesn't really do that. Yeah, so U3M bail, fprintf switches on the kind of error that you have, and yeah, just produces your result there, and then ends up with this hard-coded long jump operation that is your actual crash. Okay, event log, events.c. All right. An event is, all right, so what is an event? It's a U3 fact. Let me see where U3 fact is actually defined. It's a type def. I think it's there in Vere.h. Yes, this is the one I'm looking for here. All right, so everything that goes in your event log is an instance of this type def struct. So you have a completed event. So this is a pair of your event number, your kernel mug, which is your rapid hashes on things, the noun itself, right? So this actually gets declared somewhere. It's a pair of a date, and then the ovum is the card information that's associated with it, and then a pointer to the next event in the queue, so that you can do this as a linked list forward. The LMDB database is just it's a simple key value transactional pair database. It has two tables. It has a metadata table, and it has an events table. And the events table is simply a pair of number to a U3 fact. So there's probably some redundancy in having the event number in the fact and in the table as well, but I'm not aware of any inconsistencies that arise from that. Event log replay is interesting. So this takes place in a couple of different times, like with snapshotting, for instance. One of the most straightforward is Mars3 play. Mars3 play is what gets invoked when you actually run the playback. There's a replay function that you can play at the CLI. I don't remember what the Urbit play drops into U3 Mars play. That's all that's going on here. And so basically this is going to walk down, pulls out your actual event log. A lot of this is printer tracking, just to make sure that you actually display which events you've already done. What I'm looking for here is Mars play batch, which is in the main loop. Okay, so here's our main event. So we get to this point. There's a snapshot. There's an last event to get consistent with, and then if something crashes, it will actually retry to play it in case it's dependent on something in your system, like overall memory. Here's your main while loop. So Urbit play will let you specify that you've played up to a certain event. So you can play these back in blocks. Some of this might also be scaffolding for the epoch system when this rolls out and we actually get to start messing around with epochs in more detail. But right now we're playing up to a certain event. As long as we're below that event, we're going to keep replaying events. We're going to jump to Mars play batch. And ultimately what this is going to do then is going to replay a numeric batch of events. The batch width that was 1024 was the hard-coded value that was given there. I don't know if there's a way to override it, but it's going to replay 1024 events at a time. The disk walk stuff, is it talking to the LMDB operations? We don't need to see that. We need to see Mars poke play. So Mars poke play is how every event is actually being injected into Arvo, right? So your Arvo, you're in the middle of an event log replay. Your Arvo has a particular state, and you need to apply this event to it. You do this through Mars poke play, which ultimately is going to result in a U3V. Where's our? Where is? Oh, there we go. There's our U3V poke route. So U3M soft. This has a crash handler wrapped around it, but it's calling U3V poke route. So we saw this, right? So we saw U3V poke route last time. This is in Vortex, and this is what actually slams the knock at the address inside of Arvo. Like this is what passes that value into 22 or 23 or whatever the actual poke arm is, and evaluates that. And this is how it updates the state of Arvo one at a time. So ultimately, the entire playback, the entire event log system is just an ordered list of nouns that are a pair of the timestamp and the actual like move information. That's the ovum. And then all the playback system is just scaffolding to say, can we poke these back into Arvo one at a time as we process this? Now, there's been some discussion about the epoch system, EPOCH, recently. This is trying to solve an interesting problem. So right now, Vere has a single event log. And you'll recall that in upgrading from Vere 0 to Vere 1 and Vere 1 to Vere 2, there was a loom migration because certain things had changed in the representation or structure of the loom that allow you to handle pointers slightly differently and so forth. But there's always been a single event log and a single snapshot. So what the epoch system is going to do is it's going to give you an event and then give you events after that snapshot. And what the epoch system is going to store with each snapshot is which version of Vere ran the events. And what's going to happen is this is going to let us do replay across different binary versions when there are jet mismatches. So for instance, there are some funny jet mismatches, like in Scott and Slaw, where you can parse things that aren't really valid atoms into values, into atoms. So you can have text of something that's not exactly a valid atom, and it will parse into an atom. I don't have an example ready to hand, but this is one we've run into. And if you search Scott Slaw in the Urbit repo, the PRs and issues, you can find a fairly recent reference to that from a couple months ago, with some examples of things that break there. And so what's happening is once you have a jet mismatch, you all of a sudden have an Urbit state that might be dependent on that jet mismatch, which means that your knock and your jet may produce different values. And in a deterministic system, that's a problem. So the epoch system is going to let you batch what took place in your history in which binary, and then when you do the playback, you'll be able to do this properly across different binary versions. Now, what is not clear to me is if this means that we fall back to knock in those cases, if this means that we have to do the replay on an older binary. It's not clear to me like what the practical ramification of this is going to be in terms of doing a long replay of events across binary boundaries, as it were. But that is the capability they're going to introduce there. So yeah, that's a Vere specific operation there. Let's see. So we have so, and then we talked about demand paging, we talked about snapshot. Well, no, we didn't talk about demand paging, but demand paging is related to the structure of the loom. This means that we only need to load the pages of memory that we're using into RAM. We can leave the other pages on disk. And so this means that we should be able to write a version of Vere that only uses the memory that's actually necessary to carry out the computations that it's currently engaged in. And there have been a couple of PRs merged into Vere that have improved the memory access patterns by marking pages as clean or dirty, and whether or not they need to be tracked or written and everything. There are further improvements in demand paging that have been envisioned. Demand paging was interesting because it about 6 months ago, it opened up the dirty guard page issue that was taking place where the guard page was not being correctly updated under certain operations, and led to a deep debugging cycle around what was going on with that too. All right, so let's see. We've done Loom, we've done event log and snapshot and replay. There is IO, right? So what's taking place with IO? All right, so the king or Earth is responsible to talk to Unix. And there's also going to be IPC, interprocess communication, between the king and the serf. I'm going to keep saying king and serf. Ted was talking about Earth Mars. I'm not actually sure if that means they've actually finally pushed that or not, but I'll find out and update the notes about that. So the king needs to communicate for the veins that communicate. So there's two kinds of veins. There are the communicating veins and the landlocked veins. So the communicating veins are things like Ames and Clay. You know, Ames needs to talk over the network. Clay needs to talk to the file system. There are two landlocked veins. Which two veins do you think are landlocked? They do not ever need to talk to anything that's outside of Arvo. Think across your vein field.
Gaul maybe?
Okay,
That's
so
the
Gaul.
OS's intermediary.
So Gaul is a landlocked vein.
Isn't jail technically a landlocked vein?
And jail. Yep.
Ah.
Because jail only finds out what it needs to find out through other veins.
Through Iris, right?
Yeah, so it can call through Iris, it can call through Ames, it can call through other pieces of the system. It never needs to talk to other things, right? It's structurally secured. So this means that every other vein, Ames, Bain, Clay, Dill, Air, Iris, Con, and Lick, all have IO with Unix, with Earth. So the king is responsible for these parts. However, it doesn't make sense to get deep into what's going on with the IO drivers until we actually talk about the vein that's doing the IO. So we're going to punt on IO, and we're going to come back and cover that in each instance when we look at this. So, you know, Ames communicates over the UDP protocol, which means that the runtime has to do UDP setup and package transmission, some of these other things, even if the actual noun that represents the UDP packet is built in ames.hoon. So we'll see what that looks like when we come back to these veins and go into them in detail. We're going to start with Bain and Dill, both of which are fairly straightforward. Dill's kind of complicated in that it tries to handle a lot of hypothetical things about terminals, but other than that, it's actually a pretty straightforward vein as a keystroke handler and terminal handler. The other thing here is IPC, right? So IPC is interprocess communication. There's not really, you know, this describes a whole field of, we have two processes that need to communicate to each other, right? Like in a sense, Gaul with two agents is IPC. They're passing messages to each other and trying to figure out what to do. Urbit runtime has two categories of IPC. One of them is that there's the king serf interprocess communication, where you actually start the runtime as the king and it has to launch the serf, and then they have to talk to each other from time to time. And sometimes they talk to each other explicitly, which means they are passing messages to each other. And then there's also vein-driven interprocess communication, which are things like con.c, which is used by con and lick, for instance, with sockets. So we'll look at that when we get to con and lick. In Vere, for instance, the king and the serf do share memory directly because they have the loom. There's a shared memory arena that they can both talk to, they can both access. And it turns out that a lot of the things they kind of need to tell each other you can just do things in the loom, and you don't really have to think about it as being done by the king or the serf in a sense. But there are also parts of the system that do have to explicitly pass messages to each other. So for instance, when you start the king, it has to start up the serf. When you are doing things with the peer, you have operations that are taking place in the serf that it needs to notify the king about, so that the king can update the peer on the file system correctly. What's going to be used here is, let's go to their lord.c for this. Let's see. This is a good example of one that does a hoon-like definition here. All right. So we have this whole set of messages here, and so this part of the system, which is dealing with peers, the Lord is this communications protocol, and it defines a writ from the king to the serf and a plea from the serf to the king. This is kind of analogous to, pokes and gifts in some sense, except these can originate both ways and communicate back and forth. So, all right, so what you have here is you have a writ. So the writ has a live, which is a request to start up the serf. So you can actually, the king issues a live writ, start Urbit worker, and then you have a serf running. Then there's other kinds of things, which are like a peek is a request for data from Arvo. Sometimes the king needs to know something about Arvo, Kelvin version, for instance. A play is mainly used in event playback because you're just telling it to inject an event. A work is a more conventional computation carried out in Arvo. So this would be, for instance, no, this wouldn't be the Urbit eval stuff because that goes through a new. I'm not actually sure what would generate a work offhand.
Yeah, the eval doesn't touch the
Yeah,
kernel.
eval doesn't touch this, so I'm not actually sure where work comes from. Something to look into there, but basically it's a request to the serf to carry out an Arvo computation if you trace the logic down. And then a plea goes the other way. So a live plea is kind of like a gift. It's telling the king that the serf is up and running. It's alive. There's also a ripe, which can be issued at various points during the serf startup to tell the king what's going on. So you would imagine it issuing a series of ripes with information about events and what's, where we're at, and then it issues a live when it gets to the end. A slog is one of your side effects, right? Like this is your output request, and a flog is your debug output request. So it would go to standard error instead of standard out. But you can, pass these back to the king, and then the king has to decide what to do with them. A peek is a response to the king with a scry result. So if the king sends a peek in, then a peek comes back. We name them the same thing for some reason. Almost unprecedented in Hoon and Arvo. I guess that's why we're in the runtime here. A play is a response to an event playback request. So this is what would happen with the play that's up here. Oh, okay. So my notes for work is that work is a response to an injected ovum event. So I guess work is that we're manually injecting an event which I guess we can do.
You do it through con.c.
Yeah, so these, okay, so work is related to the con.c stuff that lick and con both tie into then.
Lick doesn't touch work.
So lick doesn't do work. Okay, so con only does work.
Con does work. Yeah. So con, it looks like con.c sends a work, sends an event injection into the surf, or from the surf. And
Yeah, yeah, that makes sense.
Yeah.
And then basically this logic, these data structures all just gets embodied in all these weird U3 C operations all the way down. But you know, writ large, this is what's happening here. If you haven't used something like Urbit eval before, you know, this would be something like echo some value and then pipe it via standard in to Ervo, and then it'll actually run this. However, it's running the ivory pills, right? It's running the ghost ship when it does this. So it doesn't know about things like hour. It just returns a find out hour. I don't know what this is. I don't have a bowl in the same sense. So it's running on the ghost ship. And so, yeah, now what we have here. Okay, these are actually going to come through Urbit eval is a little different because Urbit eval comes through Newt. Let's look at Newt. Newt are noun blobs. They have a 5-byte header, and then they have a variable length payload. And so the header has a 1-byte version tag that is reputedly almost always 0. And then there's a little endian message byte count, and then a jammed noun. So Urbit knows how to unjam this noun and process everything. And then you actually have some interesting options. Does this list those? No, it does not. Interesting. So Urbit eval has options where you can ask it to output the results as a jammed noun. Oh, that was a bad one.
so you can
Yeah.
jam it. You can jam it as a Newt jam, and you can eval, and you can queue it.
Yeah, so you can queue your input as a jam noun. And so this is one way that you can just do a very coarse. I'm talking to Urbit and I'm processing things here. Is this Mopfil, is this what you intend to do more or less with your shell?
No, I was actually just going to. So there's a noun.py,
Yeah.
which does the jamming and queuing in Python. It's like maybe 3 orders of magnitude faster.
Okay, but it's doing something like this. It's just
Yes.
doing it. It's just
Yep.
doing the jamming and the queuing in the Python script instead of at the CLI.
Exactly.
At the bash
So you don't have to
CLI.
boot up an ivory pill. You're not evaluating anything, right? You're just unpacking a noun.
Right.
Yeah.
So most of these are pretty straightforward. Let's look at Newt send. That would seem to be an interesting one. So it writes the header with the offset, you know, does a malloc of the request size, writes the header, writes everything into a buffer. So we're using UV again. Okay, so remember libuv, we saw it. I don't think we talked about it. Well, maybe we talked about it last week. But it's the main event loop handler. It's the event loop driver for the king process. And so you're writing this this buffer into the stream, and then it'll eventually get passed on by libuv when this process takes place. So this transmits a jammed noun to a task buffer for libuv. That's what's happening with this this buffer, right? That's taking place in a couple steps here. And then Newt read is where you're actually pulling the jammed noun out of the buffer and then deciding what to do with it. So you read forward from that stream. And then let's see, you decode and looks like everything then is happening in decode. Yeah, I chased this down earlier to where you're actually poking. Yeah, so you end up like having to poke into U3V and one of these somewhere in these wrapped ones here to actually get these evaluations against your reference ivory pill. All right, let's see. What else do we have here?
A clarifying question, Neil, about
Yep, go ahead.
Is this for king and serf? Is this like how they talk to one another? Or was this used for like con?
No,
and, like,
this is
hang
used
out?
for external IPC.
Okay.
So internal. Well, go ahead.
No, just go ahead. Yeah, I was. Yeah, go ahead.
Okay. So internal IPC between the king and the serf is either they share memory and so they sort of don't have to, or it's like the Lord system. And if you go to main in Vere, yeah, serf commence, then is where you end up with this. Yeah, the problem is this, I mean, they're like, oh, we're out of the ball of mud, but this stuff is such spaghetti code when you're trying to when you're trying to find these actual invocations and operations here. I think I'm looking for I don't think it's the Qzino.
What are you looking for?
Oh, I'm just trying to find the actual surf initiation. I think it's here in U3M boot.
I think it's in boot. Yeah.
Yeah. Let's see if it's smart enough to let me click through. There we go. U3M boot. Yeah, so find your loom, find your peer, allocate everything, turn on your jets, reactivate your jets, and then it passes through some of these others here. But this is what actually gets things moving as you're doing this. There's like a tracing system. There ends up being like a lot of moving pieces, moving systems in U3 when you start this thing up and you pass it around. Yeah, so kind of similar to the boot stuff that we saw a while back. One of the things I wanted to look at was I wanted to contrast the difference in life cycle between, let's look at, okay, so like if you want to melt, right? So you have an Urbit ship and you have two ways to melt. So you can bar melt. What happens with a bar melt? Well, we'll trace that in a minute. And then you can just run meld at the command line, right? So we're closer to the command line here. So let's find meld. And so it sets some global variables about what it's doing. And then it ends up at U3U meld is the function that's ultimately going to end up at. So it runs the meld. This is the meld. Oh, that's weird. Oh, it like opened it in situ. I don't know what that means. I just want to open it. All right. So then it's going to go ahead and run some other assistance functions about making sure that you have now deduplication and these kinds of things with your meld, and you've done all your memory cleanup. So you'll get your deduplication, your cleaned up memory. From the runtime that's pretty fast, right? Like it's like you pass in the command line, it goes to U3 meld, and it comes back out. On the Arvo side, if you initiate it from the Arvo side, let's start down the Odyssey here. So when you run anything with a bar, it's a hood function. So we go to meld and we say, okay, oh, this is a Helm meld. So I need to go find out what a Helm meld is. So I go to lib hood. Yeah, so there's a Helm meld, and that takes you to poke meld. And then the poke meld emits to Arvo via what vein? How does this actually go out?
Bill?
It goes out through dill as a flog. What was a flog? We just saw a flog a minute ago.
That was an error report that I'm probably misremembering.
Well, it's basically a debug printf. Right,
Okay.
like a slog is a regular printf. And so we pass this out and we go out through dill here. Let's go back out to sys vein dill. All right, so now it has calls a dump function. All right, so pass down to hey, so it's going to pass this value. Yeah, this is why. This is the part I was looking for here. This is why. So when you're going to meld from the command line versus doing it through dill, like when you meld at the command line, it just runs it against the ship and it never actually boots the ship, right? It looks at the loom and it deduplicates in the loom because it knows the noun structure. It knows U3, but it never actually boots your ship. And so with dill, you're kind of doing this mock boot event and you're passing this back through. And you end up with passing these back out. Yeah, there's our flog. And we're going to pass out. Yeah, mass is the other one here that also does memory ops. And on the other end, I don't think we end up going back through Vere. No, we don't. Let's go back up to Vere here. And let's find meld in Lord. Yeah, so it comes back up through, ends up as a flog going up. Doesn't get handled anymore here. U3 meld, return meld. Yeah. Anyway, so it gets passed back out along that line when we run it from this side. So they end up with kind of different life cycles depending on which side of this you're actually running into when you evaluate these things. Now, the other interesting thing, and this is true of mass, which gives you the current memory operation, and meld, all right? You'll notice that they went out as a flog, which means a debug printf, right? So it's in a sense, it's a request for an output. Now, what's really odd about this, when you go look at these things, is that the mass and meld operations that get run, this information that's printed here is all from the runtime. This does not occur in Arvo, and Arvo doesn't actually see this information. So now we're getting output. This is the reason we went through Flog. We're getting output because we just are having the runtime. They're basically poking it and say, dump your memory info, unify and then dump memory info. And so it does that thing, but it doesn't pass this information. This is never a noun back in there. There is currently a bounty. I don't think anyone has it right now. A couple people were taking a look at it, but I don't think it's claimed, to pass this information, this memory footprint information, back into Vere as a noun. So we're not just calculating it, we're also passing it, injecting it back into, into Arvo. Because then you can use that information to make decisions about when to melt, right? If my memory pressure gets above a certain limit, Arvo sort of doesn't know about memory pressure. But you could say, if because it doesn't know about memory, but you could definitely tell Arvo if it gets to more than 80% of my available allocation, then auto meld, auto pack, put those things together and run them back down. So that's the kind of operation that you can imagine initializing, that right now we just really can't handle. So right now that just comes out here in via C3 meld, which is the one we saw a minute ago. After running all of that, it just prints the result of that. Yeah, there's our U3U meld call after we come through this C3 meld. So this just comes through live, which is the one we saw through the Lord stuff a minute ago. Yeah, so that's some of the inter-process communication that gets involved in that. Some other things I was going to show you at the end today. I just have some comments. I'll give you some more notes on setting these things up, but since this is our last runtime specific lesson, I wanted to talk about debugging principles for Vere and Aries. So your first fallback is to do printf, right? Just output your value. There's a U3L log you can use, which actually, so for instance, here, I could say U3L log. The nice thing about U3L log is I can give it something that is that's not an atom, but I could give it a U3 atom value or a noun value, and it knows how to pretty print those things. But if you are in a crash, for instance, or you're early in your system, like you're working on some of the jet startup stuff and you haven't initialized IO drivers yet, then U3L log will not work. So you can't use it in all those cases. In the other cases, we're going to call it printf, but we're always using fprintf to standard error stream when we do this. The other weird thing about this is we have to do faz-r, faz-n to achieve line feed to do this. So where this is actually the old school line, feed line and then carriage return instead of just faz-n to get a new line. You can use other tools like GDB and Valgrind with Urbit. GDB is pretty good for working with Urbit. There are some certain processes that you need to do. You need to make sure that typically you're probably going to attach to the Urbit worker process if you're trying to debug the loom and what's going on with or jets. You're going to attach to the surf process and not to the king. You'd only attach to the king if you're actually trying to debug like a startup process or one of these outer IO processes. So there's a couple commands that I'll give you in the notes as well to set for GDB anytime you work with it to make sure that it follows forked processes correctly, and so that it doesn't totally bail on a seg fault when those happen. But you'll run into those. Valgrind is different. Valgrind is a memory profiling tool that's useful for diagnosing memory leaks and usage in particular. I have used it successfully with Urbit. It doesn't know about the loom is one of the weird things about it, and it also uses several times more memory than the native application requires. There's a PR 5161 that has some discussion about using Valgrind and trying to track down a particular memory leak at the time. But what you have to do if you're going to use, so Valgrind, because it's a memory tracking tool, it uses several times more memory than the native application requires. And then you need to either diminish the amount of memory that is allocated in disk.c, which is right. U3 disk init. Might be in the header file. There's actually, oh, you know what? They probably removed that. What I'm telling you is, yeah, I think that's actually been removed. Okay, never mind. I will remove that line. So what we actually have to do is decrease the loom size with loom, like run it at like -- loom 28 or something small, very constrained, to see if you can actually get it to work. So now that we have dialable loom size, we actually don't manually change anything to make that work. The other thing you might find yourself doing in core dev that's kind of odd is changing the surf. So if you're working on Aries, for instance, Aries is a different surf. You don't want to use Vere's Urbit worker process. So to run Aries as a surf, you need to go to U3 Lord init, and there's a value called protocol somewhere here. Oh, right here, protocol. So if you change this from surf to the full path to the executable, then it will start that. So, I would actually have to do, home, Neil, Urbit, Aries / whatever I have that to be. And so that's how I would swap to a different surf if I were going to change that. Yeah. Questions? Nikolai, you had a question there. Why shouldn't runtime just handle it? What was that in reference to?
Right. So I just heard you talking about this melt, and yeah, like trying to get back the memory usage back into Arvo, so that Arvo decides where to tell the runtime to do something. Like, why cannot runtime just take care of it?
I mean, presumably the rationale for it was that they wanted it as an event.
Okay.
That it was some sort of deterministic part of the system. I don't know for sure, right? Like you could definitely imagine a runtime that watches memory pressure and auto melds when memory pressure reaches a certain point. I could also imagine that you might want this to be pretty dialable from the Urbit side. Like hosting providers, for instance, might want the ability to, mass set this for all of the ships that are being launched on their service, but doing it inside of Arvo as a configurable quantity instead of doing it in Vere or Aries, whichever one they end up running. So yeah. Yeah, actually there's an interesting one that came out recently. I'm gonna have you do this for the homework. In the latest version of the system, there is a runtime version thread that is used. It's a thread that is used to recover values from the runtime about what your pace and your version is. How do you actually get your current version? So I'm going to have you walk back through that and figure out how is this quantity recovered? Like, how do I actually get this value down inside of Urbit when I do this? So I can actually just this is probably too old of a fake sod. Yeah, so this is too old of a fake sod, but kind of an interesting one where Arvo is retrieving this information back out from Vere. So. All right, Kimas. Any other questions, thoughts? All right, if not,
so.
oh, go ahead.
Don't think so.
Okay. Then next time we are going to go back to veins, and it is veins from here until the end. It's gonna be a lot of veins, but we'll be good.
Man. Okay. Thank you.